Welcome guys, now we discuss about the term called A-wheel tree. The term A-wheel tree is named after by the inventors G.M. Addison Welsky and E.M. Landis. A-wheel tree is a balanced binary tree which follows the concept called balanced factor. What is balanced factor? The height of the balanced factor should be within 1, 0, minus 1. If exceeds is said to be unbalanced tree. What is balanced tree? The difference between the height of the left subtree and the height of the right subtree. Now there are two variations in the balanced factor. They are single rotation. In single rotation, there is left-left rotation and right-right rotation. In double rotation, left-right rotation, right-left rotation.
Here's an example problem to show insertion into an A-wheel tree. Example 1. Construct A-wheel tree for the following sequence of numbers: 50, 20, 60, 10, 8, 15, 32, 46, 11, and 48. Step 1. Insert 50. The tree is balanced. Step 2. Insert 20. As 20 is less than 50, insert 20 in 50's left subtree. The tree is balanced. Step 3. Insert 60. As 60 is greater than 50, insert 60 in 50's right subtree. The tree is balanced. Step 4. Insert 10. As 10 is less than 50, insert 10 in 50's left subtree. As 10 is less than 20, insert 10 in 20's left subtree. The tree is balanced. Step 5. Insert 8. As 8 is less than 50, insert 8 in 50's left subtree. As 8 is less than 20, insert 8 in 20's left subtree. As 8 is less than 10, insert 8 in 10's left subtree. The tree is imbalanced. To balance the tree, first find the imbalanced node on the path from the newly inserted node to the root node. The first imbalanced node is node 20. Now, count 3 nodes from the node 20 in the direction of the leaf node. Then use A-wheel tree rotations to balance the tree. The above explanation is executed below. Step 6. Insert 15. As 15 is less than 50, insert 15 in 50's left subtree. As 15 is less than 10, insert 15 in 10's right subtree. As 15 is less than 20, insert 15 in 20's left subtree. The tree is again imbalanced. To balance the tree, find the first imbalanced node on the path from the newly inserted node to the root node. The first imbalanced node is the node 50. Now, count 3 nodes from the node 50 in the direction of the leaf node. Then use A-wheel tree rotations to balance the tree. The above explanation is executed below. We have used LR rotation. Step 7. Insert 32. As 32 is greater than 20, insert 32 in 20's right subtree. As 32 is less than 50, insert 32 in 50's left subtree. The tree is balanced. Step 8. Insert 46. As 46 is greater than 20, insert 46 in 20's right subtree. As 46 is less than 50, insert 46 in 50's left subtree. As 46 is greater than 32, insert 46 in 32's right subtree. The tree is balanced. Insert 11. The tree is balanced. Insert 48. The tree is again imbalanced. To balance the tree, find the first imbalanced node on the path from the newly inserted node to the root node. The first imbalanced node is the node 32. Now, count 3 nodes from the node 32 in the direction of the leaf node. Then use appropriate A-wheel tree rotations to balance the tree. The above explanation is executed below. We have used LL rotations to balance the imbalanced tree. Hope everyone got a clear idea about A-Wheel tree. Thank you.
So the next topic we are going to see is Dijkstras algorithm. It allows us to find the shortest path between any two vertices in the graph. So how it works is, consider this graph between the source and destination A and B, and C and D is a subpath, and it is also a shortest path between A and B. So that is what this Dijkstras algorithm says, and it uses the approach of finding the best solution so that the end result will also be the best solution of the problem. So consider this example where I have taken a directed and then weighted graph, and I consider A to be the starting node, and I consider to be a single source of this. In previous topics we have seen Prim's and Kruskal's algorithm. Dijkstras algorithm is similar to that, but it finds the shortest path tree. So that is the only difference between Dijkstras and Prim's and Kruskal's. So first consider this graph. I'll consider A to be the starting node, and from A we have to see the adjacent vertices from which A is being pointed outwards. We see B and C are the adjacent vertices, and since weight has been given, we are going to use that. I have here taken a tabular column of about the given vertices. So there are 6 vertices in this graph. So I have taken about a 6 cross 6 matrix tabular column. So from A, first one A, we don't have any self loop from A to A. So we will consider this to be 0. From A to B it is 2. From A to C it is 4. From A to B there is no direct link, and so we will take it to be infinity. And from A to E also there is no any path. From A to F also there is not any path, so we will take to be infinity. Now from this graph we have to consider the minimum value. So 2 is the minimum value. So now the next node that is going to be visited is B. So we'll take A as such, B we have to see. So now we'll take next vertex is B. So adjacent vertices of B, C, E and D. A is already visited, so we'll not consider it. So from B, D, it is 2 plus 4, 6. From B to C, it is 2 plus 1, 3. From B to B, there is no any self loop, so we'll take the same value. From B to E, 2. So 2 plus 2, 4. From B to F, there is no direct link, so we'll take this to be infinity. From these 3 values, which has the minimum value? C has the minimum value. So the next node that is going to be visited is C. So we'll write this values as such, and C is being. So for understanding, I am marking the visited nodes with boxes. So from C, what are the vertices which are adjacent to C, and the vertices which are outwards from C is only E. So now we will consider E. So from C to E, C has already the distance of 3. From C to E, it is 3 plus 3 is equal to 6. But E has 4, which is less than 6. So we will only consider the minimum value and we will write the same value as such. So we will write 4 as such. So we will write 6 and this as such. So from this, which has the minimum value, 4 has the minimum value. So the next node that is going to be visited is E. So these are already visited nodes. So we will write this as such. So from E, we have to see the adjacent vertices of E and also the vertices from which E is outwards. So only D and F are the vertices that are being taken into consideration. So E has already the value of 4. So now from E to F, what would be the value? 4 plus 2, 6. So we'll write now 6 in the place of F. And from E to D, four plus 3, which is equal to 7. But see, 6 is less than 7. So we'll write the same value as such. Now see, both have the same values. Now you can take any vertex, either D or F. That is up to your choice. I am taking D. So I'll write D. So now from, if there is any self loop for D, no, right? So we'll write 6 as such. D has the value of about 6. From D to F, the distance between them is 6 plus 2, 8. But here the value is 6, which is less than 8. So we'll write the same value. So D is already visible now. Sorry. Finally, we have the last value of F. We can notice that from F there are no other vertices from which F is being pointed out. So we'll stop with this, and finally this is the finally, since I said earlier, I am taking from a single source the shortest path. So from A to A, the shortest path or the distance between them is 0. From A to B, I am considering a single source. So it is always A to D, A to E, A to F. So from A to B, what we have? 2. A to C, 3. A to D, 6. A to E, 4. And A to F, 6. So this is the shortest path from a single source to the other vertices. See the concept of BFS and DFS. So first we will see about BFS. BFS is nothing but breadth first search. So it is a vertex based technique for finding the shortest path, and it uses Q as the data structure, and as we all know, Q follows the principle of first in first out. So consider this Q where I have inserted the elements. So this is the first element I have inserted, and this is the last element to be inserted. So if I have to pop any element from this Q, then I will pop this 10. So as we see, the first in first out, the first element to be inserted was 10. So the first element to be popped out will be 10. So now coming back to BFS. So BFS is a traversal approach in which all the nodes in same level are traversed first. So that is nothing but siblings are visited before the children. We will see this concept in the graph. And there is no concept of backtracking happens in BFS, and BFS requires more time and space complexity. And this concept is used in various applications like bipartite graph. So now consider an example of this graph where I have taken an unweighted and an undirected graph, and I consider C to be the starting node of this graph. Now what we have to do in the BFS traversal is we have to see the adjacent vertices of C, the starting node. So the adjacent vertices of C are A, G and B. As you can see, A, G and B. So we'll write C is the starting node and A, B and G. And writing this A, B, G can be of any order. You can even write as B, A, G or G, B, A. That is of your wish. Once after writing the adjacent vertices, we will next move to the first adjacent vertex of C, that is A. So once we move to A, we have to again see the adjacent vertices of A. So now the adjacent vertices of A are D and C. But we have already seen that the already visited or traversed nodes should not be included. So we will not include C and we will include only D. So now we will write D. We'll write D. Then we will move to the another adjacent vertex of C, that is B. So from B, now we have to see all the adjacent elements. From B, G, E, C are the adjacent elements of B. But as you can already see, C and G are already traversed elements. So we cannot include C, G as the adjacent vertices of B. So we include only E. So now again we will traverse to G. So the last adjacent vertex of C is G. So now the adjacent vertices of G are D, F, E, B and C. So as I already said, D, E, B, C are already traversed elements. So we cannot include in the Q. But the only untraversed element or node is F. So we'll finally include F. So this is what is BFS traversal. This is not only the solution of BFS traversal for this graph. There are numerous solutions because if we change the order of writing the adjacent vertices like B, A, G, the adjacent vertices of this order will also get changed. So there are numerous solutions for the BFS traversals. Now we will see about the concept of depth first search. DFS is an edge-based technique and it uses stack as the data structure. We know that stack follows the principle of last in first out. So consider this as a stack and I have inserted certain elements in it. Consider 12 as the first element to be inserted and 6 is the last element to be inserted. If you want to pop any element from the stack, then 6 would be the element to be popped out from the stack. Now coming back to DFS. DFS is also a traversal approach in which the traversal begins at the root node and proceeds through the nodes as far as possible until the last node. And here the children are visited before their siblings. There in BFS we saw that siblings are visited before children. So here in DFS, first children are visited and then the siblings are visited. And then DFS is a recursive algorithm that uses backtracking. There we saw that BFS does not use backtracking. And then DFS requires less memory and it is not an optimal solution for finding the shortest path. And DFS is fast as compared to BF. Now I take the same example graph as taken before in BFS. Now I also consider C as the starting node. So for DFS traversal, as we saw, we will use a stack data structure. So first I have written the starting node C. Here the difference in DFS and BFS is nothing but in DFS what we will do is only one adjacent vertex of the starting node will be pushed into the stack. But in BFS, we saw that all the adjacent vertices of the starting node were pushed into the queue. So first we will push any one of the adjacent vertices of the starting node. You can either push G or B into the stack, but I have taken A as the adjacent vertex of C and I have pushed into the stack. Then I'll move on to A and see the adjacent nodes of A. As you can see, C and D are the adjacent nodes, but C is already traversed, so I can't take C. So now I take D. So I have pushed D into the stack. Then again moving to D, I'll see all the adjacent vertices of D. A, G, F are the adjacent vertices of D. But since A is already visited, I can't take A. So either G or F. I have taken G and pushed G into the stack. And once moving on to G, I have taken all the adjacent vertices of G. But D is already visited, C is already visited. And so I have B, E, F as the options. So now I'll travel to B. So I'll now push B into the stack. And then after going to B, I'll see all the adjacent vertices of B. The adjacent vertices of B are G, E, C and E. But G and C are already visited. So the only remaining option for me is E. So now I'll travel to E and push E node into the stack. And finally going to E, I'll see again the adjacent nodes of E, and we have G, F, B. B, G is already visited, so the remaining only node being unvisited is F. As you can see, this is the DFS traversal of depth first search of this graph. So if, for example, if you take this graph to be a directed graph, then this changes. So now if I consider this graph to be a directed graph, then the DFS travel changes. Now again I consider C to be the starting node. Now I'll again traverse to A. So first A is the, C is pushed into the stack and then A. Now after going to A, we have to again check the adjacent vertices of A. Now we have to see that from A, only one edge is pointing outwards. So only one node is coming out of A, that is D. We can't take C. So the only one option we have is D. So we'll push D into the stack. And after going to D, we have to see if there are any vertices to which D points out. But we can see that there are no adjacent vertices where D is pointing towards it. So now what we do is, we'll now backtrack to A and see if there are any other adjacent vertices which are being unvisited. But we can see that there are no vertices which are being unvisited. So now again we'll backtrack from A to C and we'll find if there are, again we'll check if there are any adjacent vertices unvisited. We have G and B. So now we'll take B. So from C now we have gone to B. So after going to B, now we have to check again for the adjacent vertices pointing outwards from B. So from B, G is pointed out, E is pointed out. So we can take either G or E. I am taking G. So from G, again we have to see adjacent vertices which are pointing outwards from G. D is pointed out, F is pointed out, E is pointed out. But D is already visited node, so we can't take it. And C and B are also adjacent vertices of G, but they are not pointing outwards from G, so we are not considering it. So we are taking we can take either F or E. I am taking F. So from F, we have to see if there are any vertices which are pointing outwards from F. We can see that E is pointing, the adjacent vertex of F, E is being pointed out from F. So now we'll again finally push E into the stack. So now once after coming to E, we have to check if there are any other nodes adjacent to E. But we find that there are no other nodes adjacent to E. So now what we have to do is, we have again backtracked to F. And we have to check for F if there are any adjacent nodes that are being unvisited. But there are not any other nodes that are being unvisited. So we again backtrack from F to G. And we have to again check from G if there are any nodes that are being unvisited. But we find that there are no other nodes that are being unvisited. So again we'll backtrack from G to B. And again we'll check for B if there are any adjacent vertices, and there are not any other adjacent vertices. So again we'll backtrack from B to C. So once we have finally reached the starting node and find that there are not any other adjacent nodes, we finally stop here. And this is our final DFS traversal.
Now we are going to see how to construct a binary tree using in-order, pre-order and post-order. For in-order, we first visit left child, root and then right child. For pre-order, root, left child and right child. For post-order, left child, right child and then root. We move on to the sums. The pre-order and in-order numbers are given. In in-order, we can't find the root, so we move on to pre-order. In pre-order, the first number is considered as root, and we want to find the number, first number in in-order, 11 here. Left of 11 is left child and right of 11 is right child. Then 11 is the root here. Then the second number 12, 12 which was left of 11, so we write here. Then move on to third, 14 which was left of 11 and also left of 12, so we write here. And 15 which was left of 11 and right of 12, so we write here. Then 17 which was left of 15 and right of 12, so we write here. Then move on to 13, 13 which was right of 11, so we write here. Then move on to 16 which was right of 11 and then left of 13, so we write here. Then 18 which was right of 11 and left of 16, so we write 18 here. This was the constructed binary tree for in-order and pre-order. Then we move on to the post order and in order. The post order and in order numbers are given below. Here for post order, we considered the last number as root, 11 as root, as we find 11 here, left of 11, left child and right of 11, right child. Then move on to second number, 13, which was right of 11, so right here. Then 12 which was left of 11, so right here. Then 15 which was left of 11 and right of 12, so right here. Then 14 which was left of 11 and left of 12, so right here. Then 17 which was left of 11 and right of 14, so we write here. Then 16 which was left of 11 and left of 14, so we write here. Then 19 which was left of 11 and right of 16, so we write here. Then 18 which was left of 11 and left of 16, so we write here.